Okay, I think I'll start now with the presentation. It's about 9 o'clock. Welcome to my presentation about LEGO crash simulations in LS-DYNA, and especially about the data management for large-scale models, in this case, LEGO models. I held the same talk at the Simulation World, the DYNAmore virtual conference, just yesterday, but today I have some more content, and probably I will also show something within the real applications. Okay, so just let's start. What I'll talk today about is the scale simulation data management system, which consists of various models like status E for requirements, engineering, LoCo for the modeling and setting up models and the whole pre-processing part and getting it to the HPC system, the CAViT for browsing through huge amounts of results, and status A for monitoring the results. Today's talk will be mainly about the LoCo, the scale model part, and how to set up in this workbench for simulation engineers models from actually CAD data to the results. And LoCo is, as I said before, a workbench where you can hold all your data, can work with your data, where you can mesh your data, where you can set up your simulation, send your simulation to the cluster, view how the progress is on the cluster, and where you can actually also implement all your simulation processes. And it's solver independent. Our clients uses together with FEMcrash, LS-DYNA, Abacus, Nastran, and various different other solvers. And I also will give a little outlook into CAViT, which can be used for browsing through huge amounts of simulation results. And these is a very lightweight web interface where you can actually see all your results, filter them, look through them, see reports, compare simulations, and so on. Okay, but let's start. When did everything start? It started with this teaser by ADAC and CT, where they showed that they would do an actual real crash with the LEGO Porsche model. I have the model here. It's actually a pretty big LEGO model, and it's made out of 2,700 parts, which is quite a lot. You will need quite some time to actually build it. And CT and ADAC only showed it up to that point, and they didn't show how the crash went. But they asked, what will happen? What will happen during the crash? What will happen to the car? Will it break? Will there be LEGO bricks breaking? How will the crash look? And obviously, in our office, and especially in the office of DYNAmore, everybody said, okay, if not we, who else should be able to predict that with LS-DYNA? This is our daily business, we should do it. However, as I said before, the model is quite big. It has about 2,700 different bricks, and yet alone downloading the CAD data and opening it in tools like ANSA is a challenge, because it's many data, and meshing the 2,700 bricks is also quite difficult. So we didn't make it in time and couldn't do the prediction at that time. However, later on, I started to investigate how to set up virtual LEGO models. And surprisingly, in the internet, you can find many resources of CAD software dedicated to LEGO, and also enthusiasts putting up any kind of LEGO CAD data. Every brick, just as it appears in a new model, will be uploaded by somebody, and you can use that to create your own virtual LEGO models, as you can see here. And these LEGO models then you can use for doing renderings, photorealistic renderings. And you even can order your bricks that you need for creating the physical model, the real model, directly from within that CAD software. So there's a huge community around that. And I built myself a small prototype, created a CAD model, and I was set up. Then even later, a customer approached us and asked us whether he can already work with CAD data within LoCo and relate the CAD data directly to a meshing process. And we said, well, yes, we should be able to do that. And around Christmas, I think it was 2018, in preparation for the project, I imported my small LEGO CAD model into LoCo. I split it up into a real product structure, as you know it maybe from PDM systems. And I imported the product structure. I imported every brick as a separate CAD file. And I set up the process so that you could work with your CAD tools from within LoCo. And we also have a paper on that, but not with the LEGO model, but with real car project, which was done for a project for Audi and with real CAD parts. So if you're interested to see how that can work in LoCo with a real car, you can look up that paper, and yeah, I detailed the process there. What I also did for the LEGO models was I implemented the meshing process, because that was a requirement of the people at Audi. So what we did is we held together with the CAD data of each part in the LEGO model. We held all the necessary data or the data created during the meshing process, like the original CAD data, the converted CAD data to ANSA in form of an ANSA database file, the cleaned up geometry, the prepared geometry for meshing, different mesh representations, like different mesh sizes, like 1 millimeter, 2 millimeter target element size for the LEGO bricks, even different formats for solver files, especially the small model. I created at first the LS-DYNA simulations, but later I tried to create from the same mesh data also the PEM crash simulations. And because this is always also a request of customers, if you can do with the simulation data management, save the time if you are working with different solvers. And yes, you can. And also in LoCo, I set it up in such a way that I have a library of bricks, and I can just mesh every brick in its original position once, and then I can maintain this mesh brick in the brick library and use it over and over again in all my LEGO projects. And this kind of reusing already done work is also a very important aspect of simulation data management. So with that, let me say how to get from the CAD data actually from the LEGO CAD data to an LS-DYNA deck. To do that, because I do not want to do that over and over again, we created a small script which takes the LDraw format. LDraw is the format used by LEGO enthusiasts to represent their LEGO models. And the script converts the LDraw format actually to LS-DYNA. And this is done by transferring the positional and rotational information of each brick to LS-DYNA transform cards, and using an include transform to import the same brick over and over and over again. So if you have a model which contains just the same brick but hundreds of times, you will just store one meshed brick as an LS-DYNA keyword file, and then you will include it many, many times. And we are using include transform to offset the node and element IDs and part IDs and so on. And this script is maintained within LoCo and is run every time I want to run a simulation directly on the CAD data. So in this way, I can just modify the CAD data. And if the CAD data consists of mesh bricks, which are already in my library, I can just run the simulation directly from my LEGO CAD data, which is quite convenient. Another aspect of LoCo is that once you got all your data in, all your simulation, your meshed bricks and the CAD data for the positions of the brick, it becomes easy to set up many, many different load cases for that. For example, here you can see in the screenshot, I set up with my small scale car, different load cases for different velocities like 10 kph, 25, 17 kph, and so on, and different impact angles for the barrier and so on, and different overlap with the barrier. And once you set up your simulation, you can also integrate into LoCo the process of submitting the job to the HPC system. In our case, a small HPC system in our office in Dresden. You can also use your local resources, but it's more convenient on the HPC system. And then you can start your simulation. And what you see here on the right side are the videos of my very early simulations. Okay, at that time, I was not quite convinced about the crash results because they kind of look strange to me. So because it was winter, I decided to do a small weekend project with my kids, and we built an actual wooden slingshot-driven crash sled, which you can see here. There's a crash sled actually, and there you have a rubber band which is driving this slingshot, and you can pull the crash sled back, put the car inside, place the barrier at the front of the crash sled, and then you can let it go and crash the model. And it's a lot of fun to do that with the kids because they build the model over and over and over again and crash it all the time. I captured the test with 240 frames per second using 2 different smartphones actually. And these are the results of my initial crash tests with my initial simulations. And as you can see from these comparison videos, the results looked quite well, actually. I was surprised that they looked so well. And with that, my initial LEGO project was terminated. For me, everything was good. However, at some conference, I showed it to some guys of DYNAmore and showed them, okay, do you remember the LEGO stuff? I actually did at least a small LEGO model. And they said, okay, well, with this process, we probably could do the real thing. And that was about Christmas 2018, and I got myself the LEGO model, the actual Porsche, and we built it together with our kids in the office, and it was a lot of fun to build the model. And then we found pretty fast many people throughout the whole company of DYNAmore and Scale who wanted to help to do the real simulation. For example, Niels in the US, Pierre in France, and Thorsten, Andre, David in Stuttgart, me and Alexandru here in Ingolstadt, and also some people in Dresden who help out. And actually, most of the effort went into meshing. Fortunately, all the CAD data, as mentioned earlier, had been available on the internet. And so it was merely a thing of importing the CAD data into LoCo. And then we could start to mesh every brick. And meshing has been done, as I told earlier, by different people in the US and France and Stuttgart. And either they worked directly in LoCo, as I showed before, or they provided me the meshed bricks and I imported it into the library in LoCo. And after a couple of weeks, mostly during our spare time, we were able to mesh the 180 different bricks that we needed for the Porsche model. Also, during that time, David in Stuttgart did some testing to generate a material card for the Lego, and for that purpose, he took this flat brick and he cut out a specimen from that brick and put it into the tensile testing machine and did tests, and with that he created a MAT24 material card. And this was later used during all our Lego projects. Another thing is how to actually model the clamping force. And the clamping force is if you take like two bricks, like these ones, and you put them together, you'll know that you need a certain force to pull them apart, the bricks. And we noticed that we'll need to probably model this force if we want to get realistic results. So David put in two of these bricks into his machine, and he pulled apart the two bricks with the and measured the force, and that's the result that you can see here. And then we tried to model it by using a contact tie break nodes only card, and we put nodes on top of each stud, and if the nodes become close enough to the surface of another brick, they will stitch together, and only if a certain amount of force is exceeded, the bricks will separate. And Niels in the US set up a small model to validate that and so that the results of the small simulation become the same as that we saw in the testing machine. Another aspect is, especially with the Technic models, they are held together many times using this technical beams and this pin, and the pins are put into holes into the technical beams. And also here you need a certain amount of force to pull them apart. And Thorsten did a small model again to validate that, which consists of a technical beam and a pin, and is pulling out the pin from the technical beam. And as you can see here, while you're pulling it out, the pin gets squeezed up here. So the material property, the stiffness of the material, directly influences the amount of force which you'll need to pull out the pin. And also the friction is important because the friction between the pin and the technical beam here determines how high the force is while pulling it out. Okay, and with this and many more efforts to try to validate it, we got actually this simulation results, which you can see here. This was a quite large model. As I told earlier, it consists of 2,704 parts. The model had already 20 million elements, and on 192 CPUs, it ran about 22 hours, which is quite good for such a big model. We also then compared the result to the test videos that we found on YouTube from CT. And as you can see here, even our early simulations already fitted quite well to the test results that we found on YouTube. Actually, we had almost no information about the test setup because at that time we gathered all the information from the YouTube videos. We tried to measure the dimensions of the barrier, the positions of the cars, and also the dimensions of this guiding block that you find here below the car and things like that. So many details haven't been known to us, and still the predictions or the simulations and the tests compared very well. Okay, with that, we went to CT, which is a big German computer magazine, and asked them, okay, you are interested in high performance computing and stuff like that. So how about not only doing the LEGO crash, but doing a report about how to do simulations for crash testing? And they said, oh, well, that sounds interesting. However, everybody can do already known crash. So they asked us if we also could do something with the Bugatti, which was a new model at that time. I also have it here. This is the Bugatti, and it's an even bigger model. And we said, well, we can. And they said, how about something more? Let's do a car-to-car crash, where the Porsche will hit the Bugatti. And you have to predict the results without seeing the crash up front. And we said, well, yes, we can do that. And we took the bet, and that was when we started to model the Bugatti. As told before earlier, the Porsche already had 2,704 bricks, which were only 182 different bricks. The Bugatti has more bricks. It's a bigger model. It has 3,600 bricks. And fortunately only 74 different bricks. As explained earlier, since I'm having a brick library within LoCo where I have each brick only meshed once, I only had to mesh 74 additional bricks to set up my process. So it was actually easier to set up the model for the Bugatti than for the Porsche, even though it's bigger. And after measuring the bricks, which was mostly done in Stuttgart this time, we came out with the Bugatti model, which had 25 million elements, which is quite big. However, putting it together with the Porsche model, which had 46 million elements, this was quite a challenge because it is a real big model. Fortunately, we could do the simulations then at HLRS in Stuttgart because at DYNAmore, at scale, I do not have the computing resources to do that. Okay. I also used a special feature of LoCo, mainly to demonstrate this feature and to try it out, which is called multi-stage assembly, which is a feature which is used to couple multiple simulation and use the results of one simulation within another simulation. And here I did a fairly simple setup. Actually, I created 4 stages. And the first stage is just putting all the bricks together into one big file, which is pretty simple. However, it's easier to handle one big file instead of 500 small files. So, and then in my second stage, I just created a simulation, importing and linking the file with the meshed bricks into the real car CAD data, and with the script earlier mentioned, I created the LS-DYNA simulation file for the Porsche model. Actually, the results are linked, so whenever I add a new brick here, it will be automatically available in my simulation model later. And okay, so I did the setup for the Porsche model, and I did also the setup for the Bugatti model. So in order to create the car-to-car crash model, I imported the result of the models like Porsche and the Bugatti and imported it into my car-to-car project, which then just had to position the different cars using transformation cards in LS-DYNA. And within that car-to-car project, I created the actual D3 plot files, the LS-DYNA result files for the car-to-car crash simulation. And these result files I linked to a 4th stage, which is doing the rendering for Blender, with Blender. And it's just doing stuff like converting it to Blender, which actually takes up quite some time because the files are very big. and doing the rendering, which can take up even more time and almost as much time as the actual simulation, to be honest. And well, the outcome looks like this. This was a really huge simulation in terms of model size. It has 6,303 parts, 46 million elements almost, which exceeds the common model size of car crashes of OEMs by almost a magnitude. And we run it for 130 milliseconds on 192 CPUs and take almost 48 hours. At that point, many thanks again to HLRS in Stuttgart for letting us run the simulations there. And with this simulation result, we went to CT and ADAC and presented them and said, okay, this is how the crash will look like. And then we went to their testing facility in Landsberg, and we're lucky enough to participate in the real crash. So we were there, helped preparing everything, and could see everything. And then the real crash occurred, and then we could compare the simulation to the actually test results. And that's what it looks like. One detail which was very intriguing to me is that the wheel pauses in space here due to inertia forces. If you look to the real model and try to pull the wheel apart, you'll notice you need quite amount of force to pull the wheel apart. However, here in the simulation, it just pauses in space. And this was really impressive to me that this is also happening in the real simulation. And also other details were captured quite well by our simulation. And we were very happy that we got that close to the actual real test with our simulation. Here you can see another video which is a cut through the wheel where you can see the pin which is connecting the wheel to the chassis, and you can see how the wheel is just staying in place and the Bugatti is moved out of the wheel, which is quite impressive for me. And doing this kind of detailed investigation into the model is just only possible with simulation, and that's what simulation is so cool. Okay, and we were also asked by CT if any brick would break, and actually almost no brick got broken really. Mostly these small pins got hurt, as you can see up here. But you can also see on some bricks, you can see some damage, like here, where plastic deformation has been taking place. And if you investigate it in the simulation, you can pick out the same parts. You can also see almost the same effects on the bricks. Okay, and with that setup, once you've set up everything, you can do about any different load case that you can come up with, like this, where both cars move and hit, which you cannot do on the test track. And with having actual test data, you can even be quite confident that the real crash, if you would do it, would probably look very similar to what you get from your simulation. Okay, with this, I'm almost at the end of my presentation. What I can show you here again is a screenshot of our viewing tool where you can browse through all your result data and see the different simulations, which is called CAViT. It's a lightweight web interface. A web interface means it just runs in your browser. I still have it open here. It's just a Firefox browser. And then you can open here the the CAViT and choose your projects, and you can just browse through all your documents, like you can download your D3 plot files and look at some log files, or look at the videos. These are videos from small simulations I'm doing right now to validate something with the clamping force on the axles, and these are simulations just from yesterday. And yes, well, this is CAViT, and it's meant for browsing through many simulations. You can just filter it, and it's a lightweight access system. Okay, it is also integrated into the LoCo X desktop client, such that when you start a simulation from LoCo, you can directly access the simulation results also from within LoCo. Okay, what's next? Obviously, with this new pretty LEGO model having been released just a couple of days ago, we are only waiting for the CAD data to appear on the net, and probably I will also do the simulation of that. However, what's also next is I will use this demo cases for our further development of LoCo X and CAViT, of our simulation data management system, to validate everything, to get a good performance in our application, in a really easy to use simulation data management system. Actually, my challenge is that even kids can do LEGO simulations with our systems, because that's, for me, the democratization of simulation. So it has to be really easy to set up the simulation. And the simulation experts like us, we are setting up the whole process, and then everybody can do the actual simulations. And also, I will use this to show off a complete process where I have the CAD data until the actual results, and I have the whole process chain. And yes, I also, maybe by end of the year, I want to do a small LoCo X Cross the Bridge challenge. It will be about doing your own small LEGO models, smaller models like the scale car that you saw earlier in my presentation. And you can do everything within our simulation data management system, and maybe we will determine a winner whose car is the most beautiful and has the most fantastic crashes. And if you want to participate, you can reach out to us. Just write an email to locosupport@scale.eu, and I'll let you know once the early access and the Crash the Bricks challenge starts. Okay, and with this, I'm at the end of my presentation now. Oh wait, one more video I have, and it's the actually real crash at real speed, and you'll see it's just fast. It goes like bam, and that's it. Okay, that was my presentation. Thanks everybody for watching. Any questions?
Could you maybe tell a little bit more about the challenge that you were posing?
Yeah.
For the Crush the Brick?
Yeah, just wait, you saw in my slides earlier the smaller Lego cars. Unfortunately, I have not brought it. It's about like 200 bricks, and I'm currently setting up the setup in our demo environment, and so that once we are getting further in the development process of LoCo and CAViT, we can offer you that you can have a test license and just use our system to do small Lego simulations. You will be able to do your own small Lego cars like this size using LeoCAD, or yeah, I think LeoCAD is a good choice, and do actually crash simulations and test out our simulation environment and see how this works for you. And I'm proposing that the challenge will be who has the most, for example, the most beautiful car, and which is still performing good in a crash in the means of where the bricks are not separating too much during the crash. And maybe also we'll do small car-to-car crash with the better cars, and we will define a winner afterwards on that. So if you want to participate in that, just write us an email, and I'll let you know once we are ready to go with everything, and provide you with the credentials and everything, so you can start your own small Lego crash simulations. Has to be small because we do not have so much computing power to run the real big models, but I think the small models are also fun. And it will be done in LoCo and CAViT.
Okay, perfect. Yes, yeah, sounds like a lot of fun. I will definitely write an email.
Just let me see. I did a simulation yesterday, because in the process, I don't think you see my video right now. I have to share again. Where do I share? Here. Okay, do you see now the CAViT again?
Yeah, we can see your screen.
Okay. This is the model I'm talking about, or these are the kind of models I'm talking about. It's actually it's pretty easy to create such a model in LeoCAD. It took me maybe about an hour to actually create the CAD data for that Audi Quattro, which is a new speed champion set from LEGO. And the process in LoCo will be about creating just this model, defining the conditions of the crash, like the velocity, the angle it will hit the barrier, and things like that. And then you can start your simulation and can see how your LEGO model is performing. And the purpose of this is to have using our products, getting some feedback from you, what kind of things are working good in our products or not, and yeah, and having fun. Okay.
Okay, thank you. Yeah, sounds like a lot of fun.
It actually is.
Very nice. Thank you very much.
Yeah, you're welcome. If anybody else has a question or wants to see something, we still have more time. Maybe meanwhile, I can also show you a little bit how the LoCo X looks like, the new product we are still working on. This is a pretty early alpha version, which you see here. It's actually more or less a data management system where you hold all your data. And here I have the structure of my data. It's like a folder structure. And as you can see here, you can I have the folder where I hold the small car models, like this is actually my car, and then you can go within LoCo and directly work with your models, like using the software which I mentioned earlier, this LeoCat, it's a CAD software, where you can just open the model and work with the model. And the process is then as easy as I mentioned earlier. For example, if I go and work with the Audi model, okay, I'll make it a little bit bigger, go into the model. I can just pull out the bricks from here and can place the bricks. Come on. I think it's interfering here. Oh, I think web app is interfering with the application. It's interesting. Okay, never mind. I can place a brick like here, and then I can save back the model. Okay, I didn't saw the chat. I should. Where do I see the chat? Okay. Okay, I'll just show you the material card. Okay. Wait a second. Once I change the model, the LoCo is recognizing the change, ask me what has changed, and now I have the changed file here, and then I can just go to my load case, for example, front impact rigid wall, and let me see, 25% overlap, 30 degree, and from here I can say remotely assembly, and then it will go into my job queue and will be on the HPC system. So it's actually supposed to be pretty easy to work with that and submit jobs. And there was a question about the material model. Actually, I'm not the expert on materials, but it's a material 24 card. In LoCo, I maintain it within a material library also, which you can see here. And I think I have it here in plastics, hopefully. Yeah, this is my material card here. And I can open it with GWAM. And can take a look in the GWAM material card. Oh, it's open. It opened on the other screen. That's why I'm not seeing it. So it's actually pretty easy. Material card. We also created a material card with curves. I think David did that. But later we decided to not use that, but use instead just the this mud piecewise linear plasticity count. But if you have questions to that, you should approach maybe David Koch, because he's the expert on the material cards. Okay. Yeah, my job, which I sent to the HPC, is running right now. That's what it tells me here. And maybe meanwhile, I can show that even from within LoCo, you will be able to access the results of your simulations. And it's the same as we saw earlier on the web page. You can just go here and download your D3 plot files or open them. The good thing about the desktop application is that from the desktop application, you can directly work with tools like ANSA, Meta, Animator, and so on, which you cannot do in the web browser, or not so easy to in the web browser. But I just wanted to show here that even from within the new LoCo desktop client, you can access all the results also. So this is now a truly complete simulation data management system, from starting with working with CAD data, working with all the other simulation data, doing the meshing, and finally submitting the runs, getting the results, and working with your simulations. And LoCo is so that it's synchronizing everything in the background with all the other members that are working on the same project, so everybody can see what everybody else is working on. And if somebody else submitted a brick anew, it's instantly available for all the others.
Hello?
Yes.
This management system produced quite a few include files and a huge system of input files, which took quite a substantial part of the simulation time, was just reading the input files and just putting everything together in the simulation, in the simulation program. Do you think in the future that the simulation programs will just adapt to that and just offer more functionality to more or less optimize this kind of reading and just handling these huge numbers of include files?
You're right. Actually, even initially with the solver, LS-DYNA, we had trouble with the 6,300 include files, that it took about 5 hours of initializing. And actually, we found a way to avoid that with the solver. Using LS-DYNA, I think the initialization phase for the big car-to-car crash model is now at about 25 minutes, something like that. However, working with such a huge simulation directly in ANSA and opening it there is always problematic. Let's put it that way. Especially if you have so many include files, opening it completely in ANSA, the Porsche and Bugatti car-to-car crash takes a lot of time. And we also had issues with exceeding certain boundaries of numberings, because if you get into the range of 45 million elements, the numbering, you have to be careful that you do not get beyond the 100 million number, because then it cannot, I think beyond that it cannot be handled by LS-DYNA. But also ANSA had some problems reading such big models. Probably they will get better. However, I didn't need so much ANSA to work with the model in the pre-processing side. I needed ANSA and I used ANSA mostly for doing the meshing of the individual bricks. And then we worked mostly with the CAD files, which where there's no problem to work even with the bigger Porsche and Bugatti CAD files. And we created the simulation, and once you got the simulation and you got the results, it's no problem to open them in Meter and to open them in other post-processing tools like LS Prepost. Because there the complex structure of includes is not present. And but I think it's not only the complex structure of inputs. We also created simulation files where all the data was within one file, and it still takes a lot of time to open it up in ANSA and other pre-processing tools. And but also working with the large simulation files was a problem, because I wrote out many time steps because I wanted to have smooth videos, especially for the rendering material. And so my files, even with FEMSIP compression, ended up to be more than 23 gigabytes. And it was always a problem to transport the files and things like that. And this is also something LoCo can help with, because it's doing post-processing also on the HPC side, or it can do post-processing on the HPC side. So you do not have to transfer the huge files always. If you just want to see a video, you can avoid transporting the huge result file. Obviously, if you want to work with them in the post-processing tools, you have to transfer them to your desktop. And this is also done automatically with LoCo. If you want to, you can say when the simulation is finished, you should start right away the downloading of your job data. And this is very convenient, because mostly you start your simulation and it will end at some point in the night. And it's convenient if LoCo already starts the downloading. So if you get in the office in the morning, you already have the simulation files on your desk, which can become quite handy. But probably solver in the post-processing and pre-processing vendors will have to adapt to such large models, because I think also in the industry we are seeing every time more and more bigger models, and to some extent these big models can maybe also help them to optimize their processes.
Thank you.
Thank you, Martin, for the question.
Maybe a small side remark, if there's just a silence from our side. The modern HPC system or the supercomputers, they really rely very heavily on parallelization. So what is very special about the system is not that there is a completely different hardware, but that you had a lot of nodes. And this is the special thing. And therefore, if you go to larger and larger models, the big problem is, if you look inside, that not every part of the simulation will just very easily be parallelized. And therefore, if you just get stuck on some parts which are just run more or less sequentially, then if you get larger and larger models, you have a real problem, and this got the new hotspots more or less. And this is where we have where we're struggling more or less. So just as a small side remark, or as an addition to that.
Yeah, and you are very right about that. This is a good point, because the domain decompositioning, if you try to run such a large model with many CPUs, as you also try to do at the HRS, it's not parallelizing that good anymore, which is a known fact. And to try to compensate that a little bit, we also tried to accomplish a way where we can use within the simulation data management system the statistics of previous runs, where the previous run said, okay, this node had to wait a lot, and we can try to use that statistic to create this decomp timings .out file, which is, oh, wait, I have to download it, which is just the file containing the statistics of that, and then we can use this file in the successor simulation to optimize the amount of elements on each node of the HPC system. This is very special, actually. However, we implemented that a couple of time ago for some clients, and it's used to optimize the runtime of simulations on the HPC system. And this is also something you probably only can do with the simulation data management system, because it consistently keeps track of simulations of the statistic which is gathered here and applies the same statistic to the next simulation, so that there can be a better model decompositioning.
Great.
Actually, Martin, we could try that next time at HLRS also.
Looking forward to it.
Yeah. Because you saw in my slides what's the next thing. It's almost the same size as the Bugatti.
My question.
Okay.
You said while before that the calculation has been conducted on supercomputer and 192 processor, like something like this. And before question also was about calculation. I understand it was MPP LS-DYNA task, or as it was multi-processing, and you use LS-DYNA as the MPP, yes, on the supercomputer.
Yes, it was MPP.
MPP, it is parallelization, or SMP.
No, it was just MPP, and it was parallelized, and it ran on 192 CPUs most of the times. We also tried to run it with more CPUs, but in the end, we always used like 100.
But maybe because MPP, it, like we know, it is, but the president before asked, and I didn't understand that it was the code of LS-DYNA MPP or SMP. SMP, it is not parallel. MPP, it is multiprocessor parallel. Yes.
Yes.
And do you know which of LS-DYNA code was used in this calculation, multiprocessor, MPP or SMP?
It was MPP.
MPP, okay.
And we had to use dual precision.
Okay. And my question is, did you see that increasing CPU, number of CPU, it is linear or non-linear, increasing the runtime calculation in hours, because it is 54 hours, and for instance, half of this processor, it could be half of this time of runtime, because my experience is that it strongly depends from the K file and to the what we have inside the simulation, and sometimes up to 16 processor simulation not increase. It's stuck, and I want to know that if you add more processor, it is linearly high and increase simulation, or slowly, and adding more processor, nothing make better with the cut the time simulation. To sum up, how about number of CPU? How as to time, runtime in hours? It is linear or not? It is worth to add more processor? It is some process of constant apart 100, for instance? Do you have some experience in this?
Actually, I did not thoroughly investigation with this model on the runtime dependence on the number of CPUs. However, if you're interested in, I think you can approach DYNAmore and ask for the models and use it for this kind of benchmarking. Okay. And as Martin earlier mentioned, it depends on many factors. How this performs, and it depends on which kind of decompositioning you're choosing. It depends on how well your nodes are connected in the HPC system, and so on. And I would suspect with this model that if you double the number of CPUs, and I think Martin also run it with 380 or 340 CPUs, I'm not sure anymore. And I would suspect that it is not linear. It's at best it's not doubling, but it's maybe then 150%. It's like
slowly,
2/3 of runtime.
My experience is that up to 32 processor, then the increasing is very, very slow, and I think a lot of processor it is not worth, but in this case I was interested how it works. Yes? But thank you for this explanation. Okay.
Oh, you're welcome.
May I add something? Just about the MPP first. Actually, I ran the simulation also above 192 CPUs, up to about 1,000 CPUs. This was what I was running at the end. And the best thing was not the MPP version for me. The best thing was the new, not new, but the hybrid version. So the idea would be to combine the SMP on one node a little bit, but not for the full node. So not, let's say, on the Haswell system with 24, or with our new system now, what we have, the Hawk, it has 2 times 64, which means 128 CPUs cores per node, which is quite a lot. But what I found out is if you take a little bit SMP out of it, then you get a little bit more than just not using all the CPUs. So it was a MPP hybrid, let's say, with 2 or 4 OpenMP threads per, which was the best at my place at the moment. And then I get it down, let's say, to 18 hours or something like that. Below at least the 24 hours at the moment. The only problem was always the decomposition part in the beginning. This was a big step when this was a bit faster in the new models. Thank you.
Thank you.
I have a question, Marko. Did you use any special decomposition technique here to reduce the runtime, or did you use the standard LS-DYNA decomposition technique?
Actually, at the beginning, I used the standard LS-DYNA decompositioning technique, and then Pierre from France, he introduced some keywords so that it was decomposition just in one direction to get a better behavior. Again, I'm not so much the expert on how to deal with LS-DYNA here, so I rely on my colleagues at DYNAmore to do that. And actually, I have a paper on it on the conference on the 16th LS-DYNA conference, and there there's a picture showing how the decompositioning is affecting the model. It's mainly slicing the model in the same slices.
Okay, thank you.